Friends, very good morning to everyone. We were dealing with continuous flow reactors. We know that continuous flow reactors are varieties available which are classified into coil reactors, fixed bed reactors, and the chip reactors. Chip reactors are more useful for the low volume reactions, and the coil reactors are more versatile and economical, and hence finds its use in chemical synthesis, starting from active pharmaceutical ingredients to reaction intermediates. Further, the other type of reactor is fixed bed reactors, where there is a fixed bed of catalyst through which the reactants pass through, and during which is heated or cooled as required, and then the product is obtained. There are modification of this third variety of reactors, that is fixed bed reactors. These fixed bed reactors are also called as column reactors. There are three varieties of column reactors here. These are the modified forms of the reactors which we explain now. The trickle bed reactor is the first variety, where it has the packing material, which is the catalyst, which can be heated through the heater, the water in and water out, and also it has a cooling jacket to maintain the temperature. Here, in case of fixed bed reactors, there is one inlet and one outlet. Here there are two inlets and two outlets. Here the catalyst is fixed bed, the reactant is the liquid which flows downwards, and another reactant is a gas which moves upwards. These are useful for heterogeneous reactions, heterogeneous catalytic reactions. The gas flow upwards and the liquid flow downwards. They are counter in their nature flow. This will be helpful for the heterogeneous catalytic reactions. Another modification of the packed bed reactors are the fluidized bed reactor. It has a perforator on which there is the solid material deposited, which may be a catalyst, and the gas bubbles through the perforator, and during the process of the movement of the gas, these solid particles gets distributed and it will be in the fluidized state. As it is in the fluidized state, it has more efficient heat transfer and more efficient reaction. Another one is the bubble column reactor. It do not use any solid phase catalyst. It has the liquid in the column which comprises of the reactants, and the gas is bubbled through this liquid phase. When the gas is bubbled through liquid phase, it creates turbulence in the column, and it creates efficient mixing and also having efficient heat transfer. Bubble column reactors are very much useful not only in reactors to carry chemical reaction and also useful for biotechnological process industries. They are simple in their construction and they low shear forces, and there is no moving parts, and that's why it is more efficient, and it achieves high energy efficiency and high mass transfer. Both heat and mass transfer can be achieved. These are the varieties of reactors which are available in the market. Ultimately, the continuous flow reactors will be helpful for achieving the chemical reaction in a very efficient manner. It all depends upon the heat transfer and the mass transfer. The heat transfer is the most important factor. In there are plug flow reactors. In this plug flow reactors, this is the cross section is shown over here and the instrument is shown over here. This is also a tubular reactor in which there are coherent plugs. This will separate the column which stops or hinders the mixing of the product found with the reactants. In these tubes, the direction of flow is axial and the direction of mixing is radial. That's why there is an efficient heat mass transfer. And also the plug flow reactors, as soon as the product is formed, it will be taken out and the plugs which are adopted in between will hinder the mixing of the reactants and the products. These plug flow reactors are operated at the steady state. It is the modification of the coil reactors. The efficient heat mass transfer occurs in this type of continuous flow reactors. The heat transfer ratio is the working principle. In other words, the temperature control across the cross-sectional area of the whole reactor is more, if it is more efficient, there is more efficiency of the reactor. The heat transfer within the reactor is determined by Fourier's laws, which is represented for the following equation. Qx is equal to UA into Tp minus Tj. Qx represents the amount of heat liberated or absorbed during the process of the reaction, which is represented as watts, W. U is the heat transfer coefficient of the heat exchanger, which is given as watt per square meter Kelvin. A is the area of the reactor where heat transfer occurs. Tp is the temperature of the process. Tj is the temperature of the jacket. Both are represented in Kelvin. Heat transfer capacity of the continuous flow reactor depends upon the size of the channel. This determines the heat transfer area per unit volume. This channel size is categorized into four types. The laboratory batch reactor has the channel size of 10 to 100 meter square by meter cube. It depends upon the capacity of the reactor. For industrial batch reactors, this is in the range of 1 to 10 meter square by meter cube. In continuous reactors, which is non-micro in nature, this will be 100 to 5000 meter square per meter cube. Microreactors range from 5000 to 50,000 meter square by meter cube depending upon the size of the channel. The temperature maintenance and transfer of heat within the reactor uniformly is very much necessary for the success of the continuous flow reaction. If there is flow efficiently, then the efficiency of the reaction or the heater increases. This can be achieved better when the diameter of the channels or the coils are small. It has high heat transfer capacity. But however, it affects the flow capacity. As it is smaller and smaller diameter, the area of flow will be smaller, and thus way it can create the pressure inside the tube, and hence it can also block the tube. Some of the reactors fabrication is so complex that these microwave reactors or micro reactors cannot be cleaned, or the blockage cannot be removed at all. That's why the fabrication of these tubes size and the purpose of its use has an important role in efficient temperature control and efficient heat transfer. If this efficiency is poor, then the yield of the product is affected very badly. Not only yield of the product, the quality of the product is also affected. This poor temperature control, it may lead to boiling or freezing within the reactor. Both affect the quality and the quantity of the product formed. Further, in extreme cases, if there is poor temperature control, there will be the buildup of pressure and which can explode the reactor, and it will be potentially dangerous and destructive to equipment. That's why temperature control is the main factor in the continuous flow reactor. This are achieved by the efficient heating systems. Three types of systems are used: single stage system with high heating or cooling flux, single stage system with low heating or cooling flux. In this single stage system, it has one compressor and the 10 type of coolant, and the single system heats the or cools the total reactor. The another variety is multi-stage system with high heating or cooling flux. It has multiple more than one, two preferably, and the distribution of temperature will be more efficient. The flux is the flow of energy per unit area per unit time. The heat transfer and mass transfer can be further achieved by mixing. We have used various mixing units, and this is another important classifying feature of continuous reactors along with the heat transfer. And this mixing helps in the efficient heat transfer and also mass transfer from the reactant to the product. The distribution of heat will be more efficient by mixing. And as this is more efficient, there will be more conversion of the reactant to the product more efficiently. One of the methods of mixing is by diffusion. Multilaminar mixers use this approach. The diffusion occurs across the temperature gradient or the concentration gradient within the product. The heat transmission to and from heat transfer area occurs by conduction. But however, if the channel size is larger, mixing by diffusion is not practical. That's why this is more helpful in smaller size channels. Another method of achieving efficient mixing is by using product transfer pump. This pumps promotes the mixing. It increases the velocity of the fluid in the reactor, and this increase in velocity of the fluid causes increase in turbulence, which maintains the flow condition and hence promotes the efficient mixing and efficient product transfer. Here there is disadvantage. It cannot be used for long reactors because there will be a pressure drop and there will be a change in the flow, a change in the fluid velocity. It is useful for the smaller reactors. There are static mixers in which we use the baffles in the flow channel in between the channel to promote efficient mixing. The best another method is by using a mechanical agitator. No doubt it is efficient, but it adds complexity to the reactor. Though it is offer advantages like versatility and performance, but eliminates in long flow channels and high pressure drops, which we find in the product transfer pumps. Every mixer unit or method or procedure has its own advantages and its own limitations. Which one to use depends upon the reactor or the reaction which we use. The efficient heat and mass transfer can occur by mixing. In the next class, we will be dealing with the types of chemical reactions which are being carried out by using continuous flow reactors with few examples. Till then, have a nice day. Thank you.